Welcome back to another episode of this series where I attack Project Euler problems. So today we are looking at the third problem, which is about prime factorization, which is a very interesting subject in its own. So they want us to figure out the largest prime factor of a large number. The way to do this is probably to do trial division. Trial division isn't very fast, but factorization is not a simple problem. In fact, that factorization is so difficult makes it suitable for cryptography. So cryptography often depend on factorization being hard. Let's do this through trial division, which means basically we try all the numbers and whatever number seems to divide cleanly is a factor. Let's call it slow test division. We need to test all the numbers from 2 to the square root, because at most one number can be larger than the square root, and that will be the number that is left after dividing with everything else. So let's make a list of all the numbers that fit. Then we use the modulo operator to see if something divides cleanly. If the remainder after division is 0, then it was a divider. And then we add it to the list of dividers. So we also need to take into account that a number might divide more than once. For instance, you can divide 12 by 2 two times. So 12 divided by 2 is 6, and you can divide 6 by 2 as well into 3. So we loop until we can no longer divide cleanly. As usual, we try to figure out how long time this takes. I don't expect this to be very fast, but it depends on how quickly we can find the dividers. If they're all small, then this will be fine. Okay, fixing the program, I missed the parentheses. And I need to import math. Okay, so let's see, 13,195. And I need to return the list I created. 13,195 can be split into 5, 7, 13, and 29, which is the exact number they gave in the example. So let's try the real number, which is rather large, like billions or trillions large. So let's see. Luckily all the dividers were small. So here is the answer to the problem. 6,857. But let's try this also with an even bigger number. As you see, the program doesn't respond. Clearly I choose a number which didn't have any small dividers. So while it's running, let's talk about factorization. I think Wikipedia has a rather good article about this. So it's a long article, but it's interesting. There is a theory in mathematics that every integer can be divided into a number of prime components, that's the prime numbers. So I mentioned 12 before. You can split 12 into 2 and 2 and 3. If you multiply 2 and 2 and 3, you get 12. And you can't do this with any other numbers than 2 and 2 and 3. But how do you go from 12 to 2 and 2 and 3? That's the problem here. We can do what I did right here. do trial division, which is also listed as the first algorithm here in Wikipedia. But beyond that, it's not that easy. There are ways to do this much faster and much quicker, but they're also way more complicated. So if you're trying to factor a huge number, there are ways to do this faster. But I think this is as good as we get. So see you next time and take care out there.